Okay, in this portion, we're going to look at a detailed example of linear regression with all the calculations. The example is plasma etching. It's essential to the first line pattern transfer in current semiconductor processes. In this particular article, we get the data, and it's regarding chlorine flow, that's our X, our explanatory variable, through a nozzle is used in the etching mechanism, and then we're looking at the etch rate, Y, the response variable. Okay, so flow explaining the rate of etching that goes on. All right, here's the data, X and Y. You can see the points there. Certainly, it's desirable to do this on the software. So I'm summarizing the statistics. The sum of the X's is here, sum of the Y's. And then if you square the X's, add it up, square the Y's, square the XY product. Keep in mind that's not sum of the squares X, okay? As in SSX, it's different. So we need to find those. All right. So first off, let's go for it here. So we need to find the sample mean. So that's X bar, which is the sum of the squares X. So 24 divided by N. What's N? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a sample size of 9. So 24 over 9. That's 2.67. Again, we want to keep more places on our calculator, but we're just trying to be simple here. Sample mean, that's going to be the Y bar sum, so 312.5 over 9, 34.72. Okay, now sum of squares X, shortcut formula, just like we did on the correlation coefficient. We'll take the sum of the X squared, so I've got 70.5 plus, now I need sum of X, that's 24, squared over 9. Okay, that guy is 6.5. Now for the Y's, we're going to do 11626. I've got 0.75 minus 312.5 all squared over 9. That guy's 776.1. And then sum of squares XY is product XY, 902.25 minus sum of the X's times sum of the Y's. You can see the similarity of the formula. Okay, all divided by 9. Let's see, that guy gives us 68.9. Okay, now to get our slope, we need sum of the squares XY, which is 68.9, all divided by sum of the squares X, 6.5. That'll get me 10.6. Okay, now the intercept is here. So we're going to use Y bar, 34.72 minus, let's see, our slope was 10.6 times X bar, 2.67, and that gives 6.65. Okay, so the regression line then is going to be 6.65 plus 10.6, and that's a 0x, just using 2 decimal places. Okay, so we've got the actual line. Now, it'd be nice to take a look at it in the plot. So in your notes, I have this display. Let's turn to R. Here's how to do the chlorine flow example on R, at least to start. Data should be in the basic load of files. We've got chlorine etch rate. Here it is. Now we're going to use the usual lecture notes file. So I've got an attachment. And then instead of doing a basic plot, I have a cute little command here called scatter plot. And what it does, it automatically puts the regression line onto it. So that's convenient. It looks a little bit better than the basic one. So we'll live with that for the moment. And you can see it. Now, to get the actual commands, let's see. Here's the steps that I took in the notes there. Just run those. And you can see I've just called X and Y my appropriate variables. Here's the same commands to get SSXY, SSX, SSY that we did in the correlation coefficient, and then B1 and B0. You could take any variables and just define them XY and get this stuff. So if I just look at SSXY, SSX, SSY, B1, B0, you can see that's the handwork that we did. Now in R, the command is the same as the ANOVA to run the regression. It's called a linear model, and I'm showing in class how those two are unified. So we'll do an LM1. Etch rate is the response, chlorine is the explanatory. So run that, and if you just look at LM1, then lo and behold, we've got the intercept and the slope sitting right there for us. Okay, last thing, if you do it conventionally, plot etch rate by chlorine, then I get the basic scatter plot, and AB line is the command that will give us the line on top of that guy. Okay, I have erred in that I've switched my two variables. There we go. Put up the AB line. Moving on to the next question, we have number 2. Does the simple linear regression model specify a useful relationship between chlorine flow and etch rate? We're going to start off by looking at the coefficient of determination and move on to the residual standard deviation. So on R, we can get this number directly, but let's use it. Let's get it by hand here. So we already have the parts. SSXY is 68.92 squared. We'll divide it by 6.5 and 776.1. That's going to give us coefficient of determination 0.942, which tells us that 94% of the variation in the etch rate can be explained by chlorine flow. So this is a lot explained. Now, for residual standard error, let me just remind us that it was the difference between the actual observation and the fitted point on the line, sum of all those guys squared, and then divide by n minus 2. That's what I mean by SSE right here. And we could do that. You could find the actual fitted value and do this squaring. I'll show you how to do it on R. Makes a lot of sense. But before I do, let's just take a quick shortcut here and notice that SSE is found in this way. Sum of the squares y is the same as the sum of the squares total. Okay, so we can plug in here that SSE is sum of the squares y, which we had already 776.1 times 1 minus the 0.942. and that's going to give us 45.361. Awesome. Plugging that in here, 45.361 divided by 9 minus 2, taking our square root, we get residual squared, or residual standard deviation of 2.55. Now, let's go ahead and do that on R briefly. So in R, just moving down the file, we can hit it right here using the values we had. And I've got R, it's a 0.97, and if you just do the correlation, then that's the same value using the formula. So SSE, we've got 45.36, we had that. S directly calculated. Let's see, 3.89. We have something wrong here. N is wrong. N equals 9. And so we have the correct value. This N was from a previous calculation I had done earlier. Okay, that covers it. Now, to get it directly, we have our linear model LM1. And so if you do the $ residuals, that allows me to look at the actual residuals part of the linear model. So if I take those guys and and then I square them, that's the y minus y bar, and then add them up, divide by 7, that's the direct calculation, which we had obtained in an indirect way. Okay, next part, I've got, while these measures are good, a test should still be conducted to be precise about the question. So let's look at a hypothesis test. Okay, as we stated before, the null hypothesis of interest is slope 0. For the alternative, we'll do a two-tailed, slope not equal to 0, although you could do a one-tailed if you wanted to. In general, is it 0 or not? That's how we think of it. So we have our normality result and the t-statistic result, so all that remains is to plug in here. Excellent. So for the standard error, let's break out here. We're going to sub in our residual standard error, 2.5436. Our sum of squares was 6.5. Interesting number there. So that's going to give me a standard error of, very conveniently, 0.9984. So basically 1. Really, really nice. Awesome. So the test statistic then is going to be, remember we always do stat minus parameter over the standard error, and the statistic was 10.6, my slope. Parameter, null hypothesis beta equals 0, and then that nearly 1.9984. So that gets me a 10.619 t-statistic. Now, immediately when we consider the curve, we know it's a reject. Checking it out, on the level of B, we're sitting here at assuming a 0, and we're way out here at, what's my B? 10.60. When we go to the t-statistic level, then we're also at 0, and because the standard deviation is nearly 1, this is just 10.61. That is radically out in the rejection region. Here's a R script to get me the actual p-value. It's 1 times 10 to the negative 5th power. So it's a huge reject. Therefore, we conclude, ta-da, the slope is statistically significant. Okay, had that on R, so we're good to go there. Next up, Estimate the true average change in etch rate associated with a 1 unit increase in flow rate using a 95% confidence interval and interpret the interval. This question perhaps isn't the best worded, but when we talk about a 1 unit increase, we're talking about the slope. So this question could be reworded to say, estimate a confidence interval for the slope. That's what we want. Okay, if that's the case, then our slope is B1, and we're going to use the usual confidence interval formula. So let's just put that out and try to frame this in what we normally do. So we always have a statistic, and then we're going to add and subtract the margin of error. So the stat plus margin of error, the stat minus margin of error. That's my statistic. So this guy right here is my margin of error, which is always the t-statistic times the standard error. That's it. So nothing real complicated here. The statistic turns out to be 10.61. That's the slope. So we just need the margin of error. And the t-statistic for that guy, we'll look it up on the table, turns out to be 2.365. Alpha is 5%, and we're using a 2 for two-tailed. And the degrees of freedom that we're using here is n minus 2. So again, that's going to be 9 minus 2, which is 7. So should be pretty straightforward on that guy. Okay, now the standard error, we already found that guy. That was, let's see, 2.54. I'm sorry, we found the standard deviation, and then we found the SSX, which was rad 6.5. Okay, so we got that guy, and that product turns out to be 2.36 because this standard error had been shown to be 1. Okay, so 10.61 plus 2.36, that gives me about 12.96, 97, and 10.61 minus the 2.36, that's going to get me 2.83. That's right, 8.23. So we're roughly 8 to 13 is our confidence interval for the slope. 8 to 13. Okay, if I just depict a picture of that, thinking about it here, here's x, here's y. The actual slope here is sitting at b equals 10.6, and there's a range. It could go up to 12 or down to 8, but it's floating around in that range. That's the concept there. Okay, almost done. Now, I've got two other questions. Calculate a 95% confidence interval for the mean at a given flow rate. What that means, I'll show you in a sec. And then there's a second question, 95% prediction interval. I'm giving you the formulas here. We may get to it in class. If you want to make sure I do, please ask it. But confidence interval for the mean at a point and a prediction interval for a mean at a point. I've got a graph here. Some R scripts tell us how to do it. XY plot is the command to get this. I've got my data, my regression line. The green is the called the confidence bands. So these are called confidence bands, and they are the confidence interval on the mean. So confidence interval on mean at a point. Okay, These pink guys here are the prediction bands. So we'll say prediction bands of the mean on a point. Okay, and that's the pink guys. The pink guys are always going to be outside of the green guys. So if we suppose that at this particular point here, we want to say, what is the 95% confidence interval on the future mean, then it's this interval right there, here to here. Okay, so what's the true mean observation at that point? You could think again of the little bell-shaped curve there. That's that interval is going to contain it. If you want to ask the question, what is an interval within which I'm 95% confident a future observation will occur at that point x, that's your pink. Okay, so that's going to go the farther distance from here to here. Two different things. One is the mean of many points. The other is an interval for a single point. Okay, we'll cover that more in class. It is mentioned in the book. That gives you the R scripts you need for it. Okay, see you in class.